In this current or electricity lesson, we are going to understand what is voltage, electric potential difference, and EMF. These are lesson objectives. What is voltage? Students usually have issues understanding it as there are many similar terms such as EMF or electromotive force and electric potential difference. Actually, another term for voltage is electric potential difference, or sometimes in short for PD. It is the difference in electric potential between two locations in a circuit, such as this. So if you want to find the potential difference, you just connect a voltmeter over here, a voltmeter, and you compare this location and this location, and this will give you the potential difference, or in short, voltage. But what is electric potential? In layman terms, it's related to the electric charges, and generally the larger the number of charges, the larger the electric potential, and the SI unit is in volts. However, there are positive and negative charges, so there are positive and negative electric potential value. And neutral means that having an electric potential value of 0, so which means that thus earth or ground is considered to be at 0 potential. Electric potential is used to determine the direction of current flow, but we are using conventional flow direction, the flow of positive charges. And the direction of conventional flow is always from a higher electric potential to a lower electric potential, as illustrated by this. So you find that this is a battery, where this is a positive terminal and this negative terminal, it will flow from positive to negative. Generally, taking Earth as the 0 volts, you have positive potential, and so you have positive charges. So some small, some are big, some are less positive, but it's still positive. And you have negative potential where there's a lot of negative charges and there's less negative charges. So if you have a positive charge starting from the positive terminal, it will always flow from high positive to slightly positive to low negative and to very negative. So this is the general direction of current flow from high to low. You might find this very familiar because this is the water flow analogy. Think of electric potential as similar height value of the water tanks. So you have a high tank and you have a low tank. You could even have a negative tank. Okay, negative height tank over here. Water current naturally flows from high to a lower height tank location. And as long as the difference between the starting height and the ending height tank, the water will always flow from high to low. But however, if both tanks are of the same height, there is no current flow. Mini summary: using this analogy where height or electric potential difference and water current and electric current is similar, current will only flow whenever there's an electric potential difference between two locations. If there's no electric potential difference, no current will flow. And current will always flow from high to low electric potential. That's why we need a power source to create electric potential difference, which is a battery. It is because a battery contains a positive and a negative terminal. And the terminals have actually two different potential. So you'll see that this is positive, and over here this is a negative terminal. And the positive terminal has a higher electric potential difference than the negative terminal. Thus, when you complete a circuit with a battery using a light bulb, a conventional flow from the positive terminal to the negative terminal in the circuit. And in short, the battery will give the push to the current as it moves, as it provides an electric potential difference in the circuit. When we look at batteries, they have voltage value. So something similar to here, that's very clear. It's known as the EMF of the battery. And this value shows the electric potential difference between the positive terminal and the negative terminal of the battery. So what happens when battery connects in series and parallel? Using a simulation, you measure the EMF or potential of the battery by placing the ends of the voltmeter at the positive and the negative terminal of the battery, which you will get a voltage. So when you connect the battery as in parallel as shown, you get the same voltage no matter where it is, as the battery has the same base potential. So the base over here is the same. However, when you connect the battery in series, you place the negative end of the battery with the positive end of another battery, the potential difference of the battery actually adds up, giving you a larger total EMF. So as you can see, over here is still 9 volts, this would be 18, and this will be 27. And the total EMF would be 27 volts. Borrowing the idea of water flow from high to low, it is now easy to see why a bigger EMF will result in a higher current in the same circuit. Using a single battery, there will be a certain speed of flow from top to the bottom. However, if we connect the battery in series by stacking batteries on top of each other, there will be a greater electric potential height difference, and this causes the speed of current flow to be faster. So you can now easily visualize how a large EMF battery can cause the electric flow to be faster or having a higher current value. And now something more official. The electric potential difference or voltage is defined as the work done in moving per unit charge across the circuit. Or in short, the formula is V is equals to work done divided by the jump out charges. This seems abstract, so another way to express this formula is to bring the Q across, and the work done is equals to the number of charges multiplied by the voltage or the potential difference. In this context, what it means is that it is a work done or energy used by the battery to bring a positive charge from the negative terminal back to the positive terminal. After the charges goes from positive to the negative terminal, the battery has to do some work using energy created by the chemical reaction within the battery to bring the positive back charge up to the positive terminal again. A stronger battery can supply more energy or work done in bringing the charges back right up. It means that the battery can now raise the charges to a higher electric potential, which means that the battery has a higher EMF. Okay, using an analogy of a baby sliding down the slide, if the baby wants to play the slide again, an adult needs to expend energy to lift the baby back up to the starting height of the slide in order for the baby to continue play. A stronger adult can also expend more energy to lift the baby to even a higher height, like this. And the baby, of course, when it slides down this side, will slide down faster. In this analogy, the baby is the positive charges and the adult is the battery or the energy source of the circuit. The strength of the adult can be seen by how high can the adult lift the baby from the ground to the top of the slide. Similar to the strength of the battery that can be shown by how high can the battery raise the potential of the positive charges, which is the EMF value of the battery from the negative to the positive terminal of the battery. So this is a summary of what we have done so far. And this is a long arrangement. Please subscribe and support my channel. For my other physics video lesson arranged according to topics, please visit my blog at boringphysicsteacherswordpress.com. You can subscribe to my channel to be informed when I upload new physics video lessons. Thank you.